Okay, so today we're going to do area under a curve and maybe talk about some sigma notation, which we did all the way back when we were talking about limits and the sum. Integration and area. So this is a really big topic for calculus and integration. We talk a lot about area because area gives us total. It gives us a total amount of something. So it represents a lot of different situations. So the area of a trapezoid is given by A equals 1/2 H times A plus B. The proof of this, just in case you want to see where it's coming from, if I had this shape, and this length is A, and this whole length is called B, this is basically a triangle plus the area of a rectangle. And the area would be my height, and this length from here to here is just the difference between B minus A. And then the height of this is still the height, but this length is A. And so what that means is the area of a triangle is 1/2 times B minus A times my height plus the area of my rectangle, which is AH. When I expand this, I get 1/2 BH half AH plus my AH. I collect like terms. I have 1/2 BH plus 1/2 AH, which works out to be my 1/2 HB plus A, which is the equation that we have here. Okay, so that's the proof of the trapezoid, just in case that's new for some of you. Now we're going to use this to help us find the exact value between the area between a curve and the x-axis. So if I look at this one from page 445, it's just linear, so it can be exact values. It can be an exact, not an approximation. If we look at here, it's really just my trapezoid on its side. So when I look at this, this is my A value, this is my B value, and this is my height. So from here, how do I know the length of this height? Well, this is going to be f at 1, and this is f at 4. And that gives me my height of A and B. So A is equal to f at 1, which is 1 plus 1, which is 2. So A is equal to 2. B is f at 4, which is 4 plus 1, which is 5. So B is 5. Now with those two values, I can find the height. 4 minus 1 is 3. And now I can use my area is equal to 1/2 my height times A plus B, which is 5 plus 2, which gives me 1/2 times 21, which is 21 over 2, or 10.5 square units. And that's how we can find the area using a trapezoid. Now, when we are doing these areas and we have a curve, we would do an approximation. And so to calculate the area of a shaded region of our second one, here we have a trig equation, y is equal to sine of x. And we're going from pi over 6 to 4 pi over 6. So the first thing that we want to do is find all of our y values. So we want to know what sine at pi over 6 is, because that's going to give me this height here, which is A, again this is B, and this is H. So sine at pi over 6 is root 3 over 2. Sine at 4 pi over 6 is 1/2. And so those are our two values. Now our height is just going to be 4 pi over 6 minus our pi over 6, which is going to be 3 pi over 6, or pi over 2. So now we have our three values, and again, this is just an approximation because we do have these gaps in here that are not going to be filled. So this is just to calculate an approximation or to find the value of just this shaded region. So our area is equal to that 1/2 times our height, which we said is pi over 2, times our a plus b, which is √3 over 2, plus our half. And we're going to get pi over 4 times √3 plus 1 over 2. And our final value, our area, can be written as pi times that √3 plus 1 all over 8. And that's the value of that shaded region. So let's go ahead and try another example. So here we're just going from 1 to x, so it's an arbitrary angle. So I just want to show you this example. Again, it's linear, so we're going to use a trapezoid. So if I were to graph this function, it has a y-intercept of 1, and it goes up 2 over 1, up 2 over 1. So this graph looks something like this. Now we want to go from a is equal to 1 to some value x over here. And we want to find this area. We'll call it a of x. So we want to know what this area is. So if I set this up, remember this is a, this is b, and this is my height. So what is my height going to be? X minus 1, the difference between those two parameters. What is a going to be? Well, that's just going to be f at 1, where I'm starting, which is 2 times 1 plus 1, which is 3. B is just going to be f at x, which is 2x plus 1. So we're going to use our trapezoid area, 1/2 h a plus b, and we're going to plug in our values. So our 1/2 stays. Our h, we said, is x minus 1. My a value is 3, and my b value is 2x plus 1. I simplify, I have my 1/2, my x minus 1. I'm going to get 2x plus 4. I'm going to take out a 2, put it at the front here. I'm left with x minus 1 and x plus 2, so I took the 2 out of here. These two cancel, and I'm left with x minus 1 and x plus 2. Now I'm just going to expand that for you to show you kind of a pattern that happens. And we get x squared plus x minus 2. What do you notice about the antiderivative of this function? What would it be? Well, we know that we would have 2x squared divided by 2 plus x plus a constant. What happens to my 2's? We get x squared plus x plus a constant. What do you notice about this one and this one? Other than that -2, that constant, which I haven't shown you how to find an initial value, that is the antiderivative. And that works out every single time to find area. That is our next lesson, called the fundamental theorem of calculus. So what we notice is that the antiderivative actually equals the area under the curve. So I'm going to post a proof about how this all works, or I'll show you the proof on the next example. Okay, here goes my proof. Okay, so we want to have some general curve, some graph f of x. And I want to find the area from some value here, let's call it A, to some value here, let's call it X. So this area right here is A of X. But how do I find that value? I'm going to introduce H. Now, think about this value right here. This space right here is H. So we'll call this X plus H right here. Now, why am I introducing H? Well, let's say this line here gets closer and closer and closer to this value of X. What does that relate to? So we want to find the area as a function A of X, which means the area under the curve from X is equal to A to any arbitrary X value. So I don't need this X value to be here. It could be here, it could be here, it could be here, it could be here. So that's why I introduced that H, is that X value can move this direction or this direction. So to me, that looks like limits. So what do I mean by limits? Well, if I want to get closer and closer to this X value, what is H approaching? H is approaching 0. So we're going to set up our area as a limit as H approaches 0. Now remember, the derivative of anything, or the area, as a limit, remember that value of f of x it would be the value of my trapezoid equation, because that's what we've been using for the last few examples. So we have this trapezoid shape here. Or if I want to use this one here, remember this point right here is x plus h, and this is f of x. So we're actually going to use this little shape here to help us get the area of A of x. So we're going to use this right here. So from here, I have my 1/2 h, and then my a plus b. Well, my a is going to be f of x plus my f of x plus h, right? Those are my a value and my b value. Now, to me, as a limit, we divide everything by h. So what's going to happen to my h's? They're going to cancel. So I have the limit as h approaches 0 of 1/2 f of x plus f of x plus h. Now plug in h is approaching 0. So we're going to get 1/2. I don't have to write my limit anymore. F of x plus f of x, because I plugged in, that is 0. So that gives me 2 f of x times 1/2, which works out to be f of x. So what did that give me? My area is f of x. Now, with this, if a prime of x is f of x, then what would just the area a of x be? It would be the antiderivative of a prime of x, which is f of x. Now, if I wanted to find a at b is equal to f at b plus c, my area at a is equal to 0, because that is a starting point which is our initial condition to help us find that constant of our antiderivative, which I'll explain later. So a at a is just f at a plus my constant, 0 is equal to f at a plus my constant, and so c is equal to negative f at a. And I know this is hard to follow, this is a very hard proof to go through. In the end, what this means is that my area to any b value, so any other second value, is f at b minus f at a. And these are your antiderivatives. And this is really the fundamental theorem of calculus, which I'll also explain in another lesson. So here's my curve, and what I'm saying is if this is A and this is B, the area under here from A to B is equal to f at B, the antiderivative, minus f at A. And so that's how we're going to set this up. So I'm going to go to do an example. You don't need to know the proof of this. I will post a video with a really good proof of it. But I want to find the area under a curve, f of x is equal to x squared plus 2, from x equals 2 to x equals 4. Okay, so now we're going to put boundaries on our area. So if I just draw a picture, I know that my graph looks like this. And I want to go from 2 to 4. I want to find this area right there. So how do I do this? This is my A boundary, this is my B boundary. Step 1, integrate, okay, or antiderivative, which we worked on last week. So f of x, capital represents the integral, is the antiderivative of x squared plus 2 dx. So what do I get? I get x cubed over 3 plus 2x plus my constant. Now you're going to see what happens to the constant, why I didn't show you the initial condition and how to find c yet. It's because you don't need it for this. Step 2, area. A at my boundary 4 is equal to f at 4 minus f at 2. Remember, this is B, this is A. From here, I can now use my x cubed, my antiderivative, and I'm going to plug in that 4. Minus, now I'm going to plug in my 2. What do I get here? I get 64 over 3 plus 8 plus my constant minus 8 over 3 minus 4. Don't forget to distribute the negative minus c. And this is why we don't need to solve for c. Notice that they both cancel. And so what I'm left with is 56 over 3 plus 4, which works out to be 68 over 3 square units. And that is how we can find the area of any curve using that idea from A to B. So I'm going to do one more, a trig one with you. I'll just write it out on here. So if we wanted to find, using this idea, my screen is frozen. Okay, so I'm going to find the area under the curve of y equals sine x between x equals pi over 6 and pi over 2. So here's my graph. Okay, and here's approximately pi over 6, and here at the peak is pi over 2. So here is my shaded region. Okay, we're no longer using that trapezoid. We're finding the area using that idea that a of x is the antiderivative at one boundary minus the other boundary. So first off, we're going to find the antiderivative of sine x, which we know is equal to negative cos x plus a constant. Again, we don't know that constant because they are going to cancel. So then what is my area? Negative cos at pi over 2 plus cos at pi over 6, because it's minus a negative. We're going to get negative pi over 2 is at cos is 0 plus my root 3 over 2. And so we're going to get root 3 over 2 square units, or units squared. And that is how you find the area using this idea. I am going to give you a bigger proof using the fundamental theorem of calculus. But that is it for this one.